the system defined by the matrix 2, 5, negative 2, 4. And I'm not going to bother writing out the system this time. We know what the system looks like. The solution to the system is going to be y, and that's y vector, equals e to the lambda t x1, x2. And that implies that the determinant of this matrix will have to equal 0. The determinant of this matrix, 2 times lambda times 4 minus lambda is lambda squared minus 6 lambda. That's going to be plus 8, excuse me. And we get another 10 from this diagonal, giving us the equation lambda squared minus 6 lambda plus 18 equals 0. Using the quadratic formula, we get lambda equals negative 6 plus or minus the square root of 36, being the square of the 6, the negative 6, minus 4ac, which would be minus 4 times 1 times 18, which is minus 72. And that's divided by 2, which is going to then be negative 3 plus or minus the square root of negative 36 over 2. The square root of negative 36 is 6i. So we have negative 3 plus or minus 6i divided by 2, finally giving us the two eigenvalues. Lambda equals negative 3 plus 3i, and lambda equals negative 3 minus 3i. Now this solution is going to lead us to e to the negative 3t plus e to the 3it, which is going to be cosine of 3t plus I sine of 3t. This is going to lead us to something similar, but that sine of 3t is going to be negative in this case. We'll get to that in a minute. Let's find the eigenvectors. Okay, now I wrote down the quadratic formula carelessly. It's negative b, b is negative 6, so this will be plus, which will make the 3 here plus, and make all these real values of 3 positive. So if lambda equals 3 plus 3i, then our eigenvalue equation, our equation becomes 2 minus the quantity 3 plus 3i, 5, negative 2, 4 minus the quantity 3 plus 3i. And if you recall where all this comes from, our equation will be, for the eigenvector x1, x2, our equation will be this. Now, of course, we have complex values here, and that's going to slightly complicate the solution to these two equations, but that's really a matter of just following simple rules of algebra. It's basically an algebra 2 problem to solve these for the complex values. Still, it's something you might not have seen for a while, so let's work through it in detail. I'm not going to take the time and the space to rewrite this matrix applying the distributive law here and so forth. I'll just note the 2 minus the quantity 3 plus 3i is minus 1 plus 3i. So in multiplying our first row by the x1, x2, we're going to have minus 1 plus 3i x1 plus 5x2 equals 0. And here we're going to get 1 minus 3i. So we're going to get negative 2 times x1 plus quantity 1 minus 3i x2 equals 0. And again, I was careless. That 3i needs to be negative, just like this one is. Okay, we've made that correction. Now, this second equation doesn't look much like multiple of the first equation, but since we have complex numbers involved here, we really can't see that as easily as we could if these were real numbers. Now, the easiest way to get to solve the first equation is to just put the negative 1 minus 3i, well, add add 1 plus 3i to both sides, we'll get that x1 factor over here divided by 5. But instead, just to illustrate how we deal with the complex numbers more than anything, I'm going to do it in a little less straightforward fashion. On second thought, we're going to get plenty of practice, so I'm not going to do that. If I add this to both sides, I get 5x2 equals negative 1, well, plus 1 plus 3i times x1, so that x2 equals 1 plus 3i over 5 times x1, giving us the eigenvector if we let x1 equal 1, we get the eigenvector 1 plus 3i over 5. Now, does this equation give us the same eigenvector? If this equation is a multiple of this one, and if the eigenvalue solutions are working the way they did with real coefficients, then this equation should give us the same identical solution. So let's just check it out and see if it's so. If we solve the second equation, now all this comes from the first equation. If we solve the second equation for x2, we get x2 equals what? We're going to get a 2x1 on this side, and then we're going to have to divide that by 1 minus 3i. Now, does this look much like this? Is 2 divided by 1 minus 3i the same as 1 plus 3i divided by 5? We could verify that it is by setting this coefficient without the x1 equal to this coefficient, and multiplying both sides by a common denominator and simplifying, and we would end up with an identity. And that's a good exercise. You ought to try that. But I want to go ahead and do this in the more general manner, where we basically rationalize this denominator. So we're going to take the 2 over 1 minus 3i and multiply that by 1 plus 3i over 1 plus 3i. And then, of course, we'll have the x1 out here on the end. Now, when we do that, what do we get? Well, 1 minus 3i times 1 plus 3i is 1 minus the quantity 3i squared. 1 minus a times 1 plus a is 1 minus a squared. 2 times 1 plus 3i is going to be, I'm just going to leave it like this, factored. So we now have 2 times 1 plus 3i divided by, well, 3i squared is 9 times I squared, which is 9i, negative 9i, because I squared is negative 1. So that negative the square of 3i is plus 9, which is going to give us 10 in the denominator. And that's, of course, times x1. And that ends up being 1 plus 3i over 5 times x1. In other words, x2 is again 1 plus 3i over 5 times x1, so that this equation gives us the same identical solution this equation does. Now again, make note of how we manipulate these complex numbers. You might have to practice a little bit, especially if you haven't done algebra by hand sufficiently in recent years. Actually, unfortunately, we see way too much of algebra not having been done sufficiently in a person's whole life when they get to this course. But you have to be able to do the algebra. So you're going to have to puzzle this out if it's a problem for you. So we've got an eigenpair. We've got an eigenvalue and an eigenvector. So let's write down that eigenpair. This gives us this eigenpair, and that eigenpair implies solution E raised to the 3 plus 3i. You'll notice that my 1 suddenly converted itself into a 3, and you'll understand how that happened. So we get e to the lambda t, our solution being y equals e to the lambda t times x1, x2, e to the 3 plus 3i quantity times t, multiplied by our eigenvector 1, 1 plus 3i over 5. So there's one solution to the original system of equations. Now our other eigenvalue is lambda equals 3 minus 3i, which leads us to the equation 2 minus the quantity 3 minus 3i, 5, negative 2, 4 minus the quantity 3 minus 3i, times x1, x2 equals 0, 0. Without, I'm just going to write down what the equations are, and I'm just going to go ahead and do that off camera. And our equations become negative 1 plus 3i, 2 minus a quantity 3 minus 3i is negative 1 plus 3i, and the 5 multiplied by the x1, x2, etc. And we get the second equation very similarly. The first equation gives us solution x2 equals 1 minus 3i over 5, very straightforward algebra there, implying the eigenvector 1, 1 minus 3i divided by 5. So our eigenpair becomes the eigenvalue times the eigenvalue and the eigenvector, and that leads to the solution e to the lambda t times x1, x2, e to the 3 minus 3i t times the 1, 1 minus 3i over 5 vector. So now we have two solutions. We have distinct eigenvectors, so we know that these two solutions have to be, or the two eigenvectors have to be linearly independent, which means that these two solutions do form a fundamental set.